Hi, in this video we'll be looking at how we can use integration in our engineering applications. So let's consider something like work being done. So what is work done? Well, work done is a force. If we have a force, we've got force times distance. So if I told you that we were pushing a box on the floor with a constant force of 50 newtons, and that we ended up moving that box from the starting point to, in a straight line, let's say 20 meters. To work out our work done, we would just take that force, 50 newtons, times it by 20 meters, and we would have, we would have 1,000 joules. Yep. So we would have expended 1,000 joules, 1 kilojoule, in pushing up this box with 50 newtons uh, for a distance of 20 meters. So that's really easy if we have a constant force. So this is only true for a constant force. And if we think about it like this, if I had a force distance diagram, so F is my force, X is my distance. If I have a constant force of 50 newtons and I pushed it let's try that again. So I pushed it to 20, then my force times my distance is just like the area under that curve, isn't it? It's 50 times 20, the area of that rectangle. So the area of a force distance curve, let's say, is actually giving us the work done. It's giving us how much energy has been used in moving this box, for example. So what happens if the force is not constant? So if the force isn't constant, our force distance graph, so the force might vary distance, and it might look something like this, in which case I can't just do a force times the distance because my force changes as the distance changes. So in that case, if I still want the work done, so if I've got my force and my distance, work done is still the area under the curve. So in this case, we would have to do some integration, right? Similar to the previous video. If we want to work out the area under a curve, we would need to use definite integration, and I would need to use sort of my lower limits and my top limit. Let's say that was 20 meters there. Okay, but what we need to know is exactly how that force varies with distance. So let's have a look at an example sort of like this. So let's say we know that a force is you might see this notation, F and then dash X. That's telling us that F is a function of X. Okay, force is a function of displacement in this case. So we might have, let's do 5x squared plus 3x minus 2, let's say. Okay, and this is how the force varies with time, with distance, sorry, displacement. Let's say I wanted to know what is the work done between, let's say X was in meters, so here X is the displacement in meters. So what is the work done between 4 meters and 6 meters, let's say? Okay. Well, again, we know work done is force times distance, but only when the force is a constant force. Because we've got a variable force, what we end up having to do is integrate f with respect to x. So if I integrated f with respect to x, if you think about it, the notation is a bit like saying f times x. Yeah, f times x. So it's similar to that idea. So here we want to integrate force with respect to x, and we've got some limits as well. So if you like, let's just try and picture what this might look like. So maybe we've got something like this. So this is our force curve, and actually I want to know the area under the curve, but between x equals 4 and x equals 6. All right, well, let's work this out. Let's see what we can do. So we've got our limits. The lower limit is 4, the upper limit is 6, and we've got an equation for our force, haven't we? 5x squared plus 3x minus 2. And I want to integrate all of this with respect to x. Okay, well, let's follow those old rules that we had. So remember, if we're integrating, the power goes up. So power goes up by 1 and divide by the new power. So 5x cubed, right, power goes up, divide by the new power 3. Let's look at 3x, so this becomes 3x squared divided by 2. And here I've got a minus 2, so if I integrate that, it just becomes 2x. Okay, do you remember if we were differentiating like 2x, the gradient would be 2? So same opposite goes when we integrate it. And if you like, we can put in that plus c. However, we did see in the last video that the plus c's sort of cancel out when we put the limits in, so we don't have to write it. Okay, and here are our limits 6 and 4. Okay, we may need our calculators here to help us work this out, but let's write it out first. So the integral between with the limits 6 and 4, first of all, we need to put in the upper limits. So everywhere there's an x, let's put in 6. So we've got 5 times 6 cubed over 3 plus 3 times 6 squared over 2 minus 2 times 6 plus c. And from there, we need to take away the same thing, but with x equals 4. So 5 times 4 cubed over 3 plus, I'm just running out of space here, 3 times 4 squared over 2, take away 2 times 4 plus c. Apologies for not working out there, just ran out of space. So let's look at that first bracket. So 5, so I'm going to put this in my calculator. So 5 times 6 cubed, 5 times 6 cubed divided by 3 plus 3 times 6 squared divided by 2, take away 2 times 6, gives me, so the first bracket gives me 402 plus c. The second bracket, 5 times 4 cubed divided by 3 plus 3 times 4 squared divided by 2, take away 4 times 2 plus c, 122.666 recurring, plus c. Okay, those c's are going to cancel out. We just need to take the numbers away from each other, and I'm going to get 279.3 recurring as my area. Okay, in engineering, we can normally write our answers to 3 significant figures, so I'm going to write that as 279. This is the work done, so joules to 3 significant figures. So that would be my answer there. Okay. We could apply this in various different ways. So if we had something that, so again, we're looking at force times distance, but we could also consider something like the displacement as well. So if you recall, we had the let's have a little think about this one. So do you remember we had V was equal to ds over dt? Velocity was the gradient of the displacement graph. Acceleration was the differential of velocity, the gradient of the velocity time graph. Well, we can actually go the other way around as well. Let's say we know what v is as a function of t. We can actually say that the displacement is the integral of velocity, and velocity is the integral of acceleration. Okay, they're remember, it goes the opposite way around. So let's consider something like this. Let's say that an object's velocity varies with time with this equation here. V is equal to 4t cubed take away 7t squared plus 6. Okay. And the question might then say, can you find the displacement from, let's say, from the start to 2 and t is equal to 3, let's say. Okay. So in this case, we know velocity is a function of time, and we're looking for the displacement. So we're thinking about this idea over here. So can you identify what we might be able to write down? So our displacement S is going to be the integral of 4t cubed minus 7t squared plus 6, and we'd put in dt. So basically it's the same as what we had before. It's just that instead of x's, we've got t's, we've got time. So velocity times time is going to give us a displacement, right? Speed times time is distance. So using that idea. What are our limits? Well, we're doing it from the start. So what is our t value at the start? Oh, it's t equals 0. So our lower limit will be 0. The upper limit is going to be 3. So we can actually do our integration here. So let's integrate what's inside over here. So power goes up by 1, divided by the new power. So 4t to the 4 over 4. So the 4's cancel there. We've got 7t cubed over 3. And then again 6 goes to 6t. Okay. We can have that plus c, but remember we know that we said if you've got limits, they cancel out. So 3 and 0. Okay, let's put in our limits. So first of all, we put it in the upper limits. So we've got 3 to the power of 4. Take away 7 times 3 cubed over 3 plus 6 times 3 plus c. So there's our first bracket. Let's do the second bracket. So this is with zeros. Well, 0 to the 4 minus 7 times 0 cubed over 3 and 6 times 0 plus c. So again, let's put in our values. So let's use a calculator here. So 3 to the 4, take away 7 times 3 cubed over 3 plus 6 times 3. So here we have 36 plus c. The second bracket, I've got all the zeros plus c, so just a plus c. So our c's are going to cancel. Plus c take away plus c. C's cancel. We're left with 36. And assuming that the velocity was in meters per second, our times in seconds, our displacement would be 36 meters. Okay. In the next video, I'll have a look at one of the past paper questions or the sample assessment questions where we need to use integration, but I think it's quite similar to what we've seen in this video here.